Hello, and thank you for joining us. My name is Ashley, and I will be your moderator for this session. During today's webinar, we will be hearing from two Eddy Covariance experts. Let's give them a chance to introduce themselves. First, we have Dave.
Hi, I'm Dave, and I'm the product manager for our Eddy Covariance products.
Thanks, Dave. Now let's hear from Israel.
Hi, this is Israel, Applications Analyst at LI-COR.
Thank you. Our webinar today is titled Using Biomet Sensors in LI-COR Eddy Covariance Systems. We will begin with an overview from Dave. Dave?
Hello, and welcome to our new Eddy Covariance webinar series. It's good to see a lot of you again. I see a lot of familiar names here. I want to thank you again for joining us. We're looking forward to another series of webinars where we can communicate with within the community, share ideas and information about Eddy Covariance method, and learn from one another. This is a new three-part educational webinar series dealing with the Eddy Covariance method. Last year, many of you may have seen the 5-part webinar series that we looked at the overall Eddy Covariance method. This new 3-part series will build upon that last series and enhance some of the information with some more suggestions and education. Again, you can find our original Eddy Covariance webinar series on the web at that location shown here. And this takes you through all the important steps and considerations to conduct Eddy Covariance measurements. As a reminder, LI-COR, we continue to collaborate and participate in the Flux community. We have a strong scientific team with years of education, experience, and publications. The team is here to support you through any questions you have. You may have seen them at scientific conferences or throughout the webinar series here as well. And all of them have been involved in these webinar series. Okay, so let's begin today, webinar series, the first of the 3-part series. This presentation here will provide information that can allow you to simplify and verify your fluxes through the use of Biomet data. Again, I am Dave Johnson, and I'm here with my colleague Israel. So here's the outline we plan to follow. I will talk about the first point on the importance of Biomet data, and Israel will cover the second 2 points later on in the presentation. First, I would like to ask a poll question here. This is the first one, so I would like to find out how much the attendees here know about the Eddy Covariance method.
Thanks, Dave. I put the poll question up on your screen now, and it reads, how much do you know about the EC method? There are 5 answers to choose from. Just go ahead and click the radio button next to your answer choice and hit submit, and we'll give everyone just a few moments to finish. All right, we'll go ahead and close the poll now. It looks like most of you have submitted an answer. Thank you. Dave, go ahead.
Okay, thank you for sharing that information. I see we kind of have a lot of different backgrounds in attendance. That's good to see. So what are Biomet sensors? These are sensors used for monitoring the environment, both the biological and meteorological functions. Usually not all sensors or measurements are actually meteorological sensors. For example, soil moisture probes and soil heat flux probes are not these types. So we use the term Biomet to cover all these. Typically, these kinds of measurements are made once per second up to 60 times, or once every 60 seconds. Here's a picture of the 10 key measurements for Biomet data. We have net radiation and solar radiation, PAR, air temperature, and relative humidity all up on the tower. We have a precipitation gauge to measure rainfall. And then we also have probes for measuring in the soil, which includes the soil heat flux plates, soil temperature, and soil moisture. So the question is, why do we need additional Biomet sensors? Already we can calculate flux measurements just from the sonic anemometer and the gas analyzer data. So what kind of benefit do we gain from collecting the Biomet data? So there are 4 key points here to take Biomet readings. The first one is to have quality assurance and quality checking of your data. And we can do that through the energy balance closure, and I'll talk about that in a little bit. We also can use this data to record the weather to help explain site behavior. So your environment's going to react and change and be affected by things such as rainfall, solar radiation, temperature. The third point is to use this data for gap filling. And this might be when your instrument fails or when your power goes down. And the fourth point is to help enhance your flux computations. So some of these values can actually be plugged into the computations that you use for getting your flux values. So here's a picture of the energy budget. That top equation, all the terms are in units of watts per meter squared. So on the left we have our net radiation flux, and then we have H, a sensible heat flux, LE for the latent heat flux, G is our heat flux within the soil, S is the rate of change of heat storage. Now this is between the soil surface and the level where our Eddy Covariance instruments are. And then we have Q, which is the sum of all the additional energy sources and sinks. So we can rearrange this equation by looking at this energy balance closure. It's actually based on one of the first laws of thermodynamics, and it requires that the sum of all the estimated latent and sensible heat fluxes be equivalent to all the other energy sinks and sources. Okay, so we can usually when we look at this equation, we can also assume that Q and S, they're typically neglected just because they're pretty small terms. They're also a little bit harder to measure. As a result, we have a new approximation or equation here. And now when we look at it, any imbalance between the remaining, we call the independent measured terms, those are on the left-hand side, and the dependent values, which are on the right, and this would indicate there's an inaccurate estimates of your flux. So here's just a quick graph to show you the partitioning of the available energy to kind of get you a view of the different values you can expect for sensible heat, latent energy, the soil heat flux, and the net radiation. You can also see at nighttime the values change because they're changing directions in which way those fluxes are going. Also, the magnitudes can be quite different. So how can this energy budget and the energy balance closure help us? First off, it's a great tool for verifying eddy covariance instrumentation. For example, your gas analyzers and your sonic anemometers, and to make sure they're working accurately and they're installed properly. And in turn, this helps verify that your final computed flux values are correct and accurate. And so we can do this by doing the QAC, and we investigate relationships between the half-hourly estimates of all the dependent flux variables, we call those LE, the latent energy, and the sensible heat flux H, against the independent derived available energy. For example, the net radiation and the soil heat flux. So what we can do is you collect these data, as I said, in half-hour value intervals, and you can make a plot. So on the y-axis, you would plot your sensible heat and your latent energy, and on your x-axis, you plot the net radiation and the soil heat flux. Now, if it was an ideal closure and all the sensors and everything was working correctly, the slope would be exactly 1, and the intercept would go through 0. However, if you can see the graph on the lower right, if it's not ideal, there could be a lot of reasons for that. Here you can see the slope is not on the 1-to-1 line, and you have a scattering of points. Could be due to sampling errors, systematic biases, neglected energy sinks, several other things, and we'll talk some more about those. So first off, we want to be able to measure all the components of the energy budget. First off, we look at the sensible heat flux. This is the heat transfer and is computed from the vertical wind speeds and from the sonic temperature. Both of these are measured by the sonic anemometer. I show a couple models there. Next, we need to be able to measure the latent energy, typically caused by evaporation as that's a major form of cooling for the plants. And it can be measured through the use of a gas analyzer that can measure water vapor. So here's a graph depicting some typical values you might see. This shows the daily variations in both the latent energy and the sensible heat. This was in early spring from a site that Lukong Xu was studying back in 2003. You can see on the sensible heat flux where there was a problem with the data with that sensor on the third day. So being able to monitor these is important. So now we look at the independent variables. We start out with measuring the net radiation. And we can do this with a net radiometer. There's a couple versions of net radiometers. We have 2 shown here. These are commonly used in the Eddy Covariance community. These particular sensors are manufactured by Kip and Zonen. And we have a single component one, which just gives you the net value. And then you have a pretty complex one, which has 4 components, and you can get all different kinds of shortwave and long-wave measurements from that. And again, in a later webinar, our second one, we're going to detail all the sensors, the specifications, and how to install them. So it'd be great to be able to attend that if you can. Now we look at measuring G, the soil heat flux term. To do that, we use soil heat flux plates. So these particular sensors, they're manufactured by Flux. You typically bury these sensors at about 4 centimeters beneath the surface in a horizontal position, and they measure the vertical flux of heat within the soil. The bottom one shown, the blue one in that picture, is actually a self-calibrating model which you can use to help get more accurate soil flux measurements. Okay, so now we are able to measure all the energy budget components using those sensors we just talked about. So what can an energy balance calculation tell us about the quality of the measurements? Both the high-speed flux measurements and also the slow energy measurements. So we turn back to this question and the tool of using the energy balance for QA/QC. So a lot of the studies, for example in FluxNet, when they look at these values, there's been some concern developing because the surface energy fluxes of latent energy and sensible heat are quite frequently underestimated by about 10 to 30%, especially relative to the estimates of the available energy flux, which is from the net radiation, the storage term, and the soil flux. And you can see in the graph how if you fit a line through the red data points, you can see that slope is not on the one-to-one line. So why is this? What are some things that can cause this? So the Eddy Covariance community really delved into this, and there's been quite a few papers on it. Among others, one of the ones that contains a lot of really interesting data was written by several authors in the FluxNet community, mainly Kel Wilson at Oak Ridge. I think Mark Aubenet from Belgium was in there, Dennis Baldacchi from Berkeley, and many other authors. And what they did is they did a comprehensive evaluation of energy balance closure. And they performed this across some 20-plus sites, looking at about 50 site years worth of data in the FluxNet. So they looked at all different kinds of things. For example, they looked at the role of canopy and the ground heat storage. And this is an interesting point that when they looked at sites that had tall vegetation, say generally taller than 8 meters in height, they had about 26 site years worth of data to look at. And they actually looked at including the S, the storage term. Again, this is the term I talked about earlier between the soil surface and up to the air, up to the instruments that are doing the Eddy Covariance measurements. So it includes both the biomass and the air. And what they saw is when they actually included this term, that the slope increased by about 7%. So now they kind of have a lot of recommendations in forested sites that it's a very good variable to also collect with your other ones. And you can do this using something like a vertical temperature profile system. and get those measurements. They also looked at, for example, grasslands, agricultural, and chaparral sites. What they noticed there is that the soil heat flux increases the average slope by about 20%. And it kind of makes sense when you have the short vegetation, you have a lot of direct sunlight coming right onto the soil surface, where in forested sites you have a lot of shaded areas underneath trees and things like that. And in the forested sites, the slope only increased by 3%. So when you're thinking about collecting this kind of data, and the heat flux makes a large portion of the energy balance, you might want to consider having additional probes to make sure you get accurate measurements there. They also looked at vegetation type, vegetation height, analyzer types, and pretty much they didn't find any real conclusion that created these energy balance differences when they looked at open and closed path analyzers, whether they looked at flat or sloping terrains, and the vegetation height didn't really seem to have any conclusive data either. So in the end, they kind of determined there seemed to be maybe 5 big areas that could cause this imbalance. And so the first potential imbalance points to errors associated with sampling. This includes things like mismatching between the flux footprint and the sensors when they're measuring other components of the energy balance. You can have some pretty big errors. For example, I think they were saying the random errors can be up to 40% for the soil heat flux term in some conditions, and you're not likely to see those kinds of errors when you're measuring the net radiation. And generally that's because you're looking at a larger source area, and that's frequently the dominant available energy term as well. So let's look at that. I put together a graphical picture here, obviously not using real photographs so I could illustrate the point. But let's look at a site here, and imagining we have a cornfield on the left and a soybean field on the right. We have the wind direction from the left. Fluxes are being measured from the corn on the left-hand side of the tower. And the radiation is also being measured on the left. So the source area here for both areas are the same. Now in the bottom picture, the wind is coming from the right, a new direction. Now the fluxes are being measured from the soybeans on the right side of the tower. However, if you look at the radiation, it's still being measured on the left, in the corn. In this case here, the source areas are different for each measurement. In addition, Thomas Foken came out with a paper, I think it was titled something along the lines of Energy Balance Closure Problem, and did kind of an overview back in 2008. He made a point that the area that the net radiometer is, let's say, seeing or measuring is much smaller than the footprint area from which all these fluxes are coming from. And so he attributes a lot of this energy balance closure to scaling problems. So the same issue applies to both issues I just described when using the soil heat flux probes as well, and those measurements. And problems can be really amplified if the canopy or the vegetation is more heterogeneous. So let's look at the next cause of an imbalance. This is a systematic instrument bias. So there's a couple examples here we could say. Say for the analyzer and the sonic anemometers, there could be biases due to improper installation, maybe wind disturbances from the tower they're mounted on, things like that. For the Biomet sensors, a few examples could be differences in thermal conductivity between the soil and the soil heat flux plates. You could have other sensors that are drifting, maybe they're not calibrated properly. And positioning and or leveling of the net radiometers is another one. So here's another illustration of problems that can result in having an unlevel net radiometer in this case. And it can cause bad measurements both on the top, above the sensor, and below the sensor. So you could be, for example, you're too close to the tower, and your instrument is going to see or measure the tower. You can see the field of view coming down and hitting that. A lot of times when we've traveled and looked at research sites, we've seen walkways trampled vegetation, instrument shelters, ladders, scaffolding, all around the base of the tower. And it happens to be right below the net radiometer. So you're going to get all kinds of crazy values from there. In addition, if you're not pointing in the right direction, for example, if you're in the north hemisphere, you want to point your net radiometer towards the south. In this picture, it's pointing in the wrong direction, and the sun is going to cast shadows from both the sonic anemometer and the analyzer onto the top of the net radiometer and cause some problems there. So the final 3 points here I'll cover could also be causes for the imbalance. The first one is the neglected energy sinks. So this could be anything from heat storage between the buried soil heat flux plates and the surface of the soil. It can be due to neglecting the heat storage term S that I discussed earlier between the soil surface and the flux measurements on the tower. Even photosynthesis is a form of biochemical energy storage. And even though it's pretty small, typically on the order of 1 to 2% of the available energy, but it could be quite a bit higher if you're looking, for example, at agricultural plants. Low and high frequency loss of turbulent fluxes is another possible cause. That might be caused due to extremely long tube lengths, for example, in a closed path analyzer system. And the long tube lengths create tube attenuation, time lags, and some other issues. Typically, they're thought to be pretty small and correctable, but still something to consider. And the final one, the horizontal and maybe vertical advection of heat and water vapor can occur. And the theory is that during times of weak turbulence, especially on terrains that are sloped, you could have drainage flows that occur. And usually air masses are moving horizontally out of the footprint. So now we kind of look at the summary of the energy balance closure. There's a lot of implications that this can have on the CO2 and the water vapor fluxes. A lack of energy balance closure, if everything's hooked up right, could indicate that the fluxes you're measuring are in error. It might not be conclusive, and again, that depends on the errors in the energy balance calculations, whether they're independent of the CO2 flux estimates or not. But if done properly, the energy balance closure can be a useful tool in verifying the proper CO2 and water vapor measurements and the subsequent computed fluxes. So I just want to wrap this portion up with 5 points to remember with the energy balance closure, and that flux sites in general have a hard time closing that energy balance. So if your site is having that, you are in the majority. The mean imbalance is on the order of 20%. When looking at energy balance, you're going to typically have poor relationships during the nighttime periods. And the best time to look at it is in the afternoon, because even in the morning you're having a lot of shifting of energy as the sun comes up and the winds begin moving. Again, there wasn't any conclusive differences between open and closed path analyzers, nor with sites on flat or sloping terrains. And typically energy imbalance persists throughout the whole year, but you generally get a better slope, closer to 1, during the warmer seasons. And finally, the energy balance closure can be used to help verify that your CO2 and water vapor flux measurements, all the components need to be measured properly to indicate when sensors are causing errors in the actual CO2 and H2O measurements. Okay, looks like we have a question from the audience.
Thank you, Dave. I do have a question from the audience, and it is, how can we determine the power needed for these sensors?
Okay, that's a good question. It really depends on the package, the number of sensors, which ones you're using. But we actually have a table that we can distribute, and we've actually have a really cool feature on our website. You should go there and look. On our Eddy Covariance pages, we have a design your own system feature on the web there, and what you can do is select the different sensors and analyzers and everything like that, and it will give you the actual power requirements to help you determine, for example, how many solar panels or batteries you might need. Okay, I'm going to continue on here. So we hit our second point on why we want to take our Biomet measurements. This one is for recording the weather to help explain site behavior. And here's an example of air temperature and the relationship between that and the flux of CO2. This is useful when you're doing day-to-day comparisons. Why were my fluxes lower yesterday than they were today? Well, you can look at the temperature as a quick view of that. Maybe between spring and fall, looking at different times when the temperature changes. You can even notice here that the shutdown, when the temperatures get very high, up above 35, close to 40 degrees C, that the stomates are shutting down, trying to preserve water. So here's some interesting data. We have measurements from a soil CO2 flux system. This was actually taken with our LA-8100 and 8150 with the 16 chambers multiplex system. This was out in a cornfield here in Nebraska. It was kind of interesting. We were collecting data. On the left hand, the y-axis, you see our flux. All the values are between, say, 1 and 3 going along. On the bottom, we have a day of year. And all of a sudden, all the data just kind of explodes, some of it positive, some of it negative. We look at the temperature, it looks okay. So our first thoughts here are there's some kind of problem with the system. Did the power go out? Did a mouse chew through the cable? Was there a power surge, something like that? And then we actually went back and looked at the weather data. What you see here is that weather events can affect the fluxes. And during that time, when the data just went in all different directions, it was due to a rain event. And the soil moisture gets affected by that. And the CO2 flux, in turn, from the soil is changing. And some of it goes high, some of it goes low, and it all depends on the soil itself. If you have mulch there, maybe there was bare soil where the water drained out quickly. So that's why you kind of get this big scattering, and it was pretty interesting, but it helped answer a question that a lot of these times it's just Mother Nature causing these kinds of events. And if you're looking at your fluxes from an ecosystem level, and suddenly you have a jump in your fluxes and you don't have the rain precipitation data, you wouldn't have a good way to explain that. So there's sensors you can use for measuring precipitation and soil moisture. We have tipping rain buckets. You can use different varieties of soil moisture probes to do that as well. And okay, it looks like we have a second question coming from the audience. Ashley, do you want to go ahead and read me that too?
All right. The question is, it looks like several companies make these sensors. Does LI-COR sell them too?
Okay, yeah, that's a good question as well. A lot of these sensors are ones that we do resell here at LI-COR. In fact, all the ones I'm using in the presentation today are ones that we actually resell. And so we get these directly from the manufacturer and package those together. I'll talk about those in a little bit. Okay, now we headed back into the presentation. The third point here on the Biomet readings is looking at gap filling. So this is typically when an instrument has a problem, maybe the power fails, and we'll look at this slide here. So some of the typical reasons you might get gaps in your data could be due to a sensor failing, a power supply issue, maybe the data's flagged for bad quality, low U-star writings, maybe rain, and you have spikes in the data. So on the right-hand graph with the red dots, you can see small gaps in the data. Now those ones are pretty easier to gap fill, as you can use interpolation and maybe get some average values between those points and fill that in, so you can still get a good value of whether the ecosystem was a sink or a source that day. If you don't have all those values, it makes it very hard to do an estimate here. Now, if you look at the bottom graph with the blue dots, this one is on a larger time scale. Looks like about 20 days there. And you can see a big gap right in the middle. Now here you can't just interpolate. You can't draw a line across the middle because you're going to have a bad estimate. And if you're trying to figure out how much CO2 is taken up or released in an ecosystem over an entire year, this gap is going to cause you problems. So how do we rectify that? So we look at two specific variables, measurements. The first one we look at is PAR. This is the photosynthetic active radiation. Now if we plot this on the right-hand graph I'm looking at, the x-axis is the PAR values, the sunlight, and the y-axis is the flux of CO2. And you can see, even though there's a fairly good scatter, you can still be able to get a pretty good fit through that data. And that builds a nice relationship. On the bottom left graph, you can see that we can look at soil temperature. It's actually plotted in Kelvin on the x-axis. And on the y-axis, we have the respiration. And here again, you can see you're able to model and get a fit through that data. And so now what you can do is you can model your CO2 fluxes using PAR, and your respiration can be modeled using the soil temperature. So now we go back and look at the gap filling techniques again. There's 4 or 5, there's many actually techniques, but here are 5 common ones. You can look at mean diurnal variation, you can use lookup tables, there's artificial neural networks, nonlinear regressions, and process models. But I'll look quickly at the D there, the nonlinear regression. And what you can see is those are the 2 models we just explained, the one using PAR and the one using the soil temperature. And we can get NEE, and we can get the soil respiration. Now if you look at that bottom graph on the right, you can see that we were able to model the red line and fill in that gap. And you can see even as it traces through the blue dot, the blue line as well, you can see that it's a good fit and a good correlation. Now you can use those points that you just filled in and be able to get your accumulation of carbon over a year. So we need those sensors to make those measurements. So here we have a photosynthetic active radiation sensor measurements, or using the quantum sensor. Here at LI-COR we have the LI-190. And then we also have a sensor for measuring the absolute global solar radiation using a pyranometer sensor, which is the LI-COR LI-200. And then soil temperature was the other variable. We recommend using soil thermistors. These are popular for measuring temperatures in the soil because they're very robust. They work out better than thermocouples. Okay, my final point before getting ready to turn over to Israel is how we can use some of these variables for enhancing our flux computations. And I mentioned that some of these values can be substituted into the flux computations in the software. So let's take a quick look at this. Here's a picture of a Eddy Covariance system. The circle I've drawn there is the height where the flux measurements are made. You have your analyzers, your sonic anemometer. Now, the LI-7500, for example, or the gas analyzer, will make measurements down near the box. That's where the control box is where we originally put the thermistor for making these measurements, typically because we use that mainly for when we do calibrations, and it's kind of a slower sensor. It's shaded down there, and it allows us to do conversions from density to mole fraction. In any case, that is where the temperature is made, and as you can imagine, the temperature down near the bottom might be different than up near the top. Maybe it's hotter in the middle of the day because it's closer to the soil. So what ideally you'd like to do is measure the air temperature up where the measurements are being made for eddy covariance. And you can put that sensor up there. You can see that in the picture shown. In addition, if you were able to have a sensor that's ventilated, measuring temperature and humidity, you can get more representative measurements of the air temperature required for the air density computations. These are the unit conversions and the WPL correction terms. In addition, you can see that graph that Relative humidity has an effect on these measurements, and you can use that data to help you with your spectral assessments. So again, the sensors for those two, the temperature and the air humidity. This is a probe, the HMP155. It's manufactured from Vaisala, and it's placed in a shield shown in the picture on the right to allow the sun from shining, keep the sun from shining on it, and allow airflow to go through those vents there. Finally, another way to help with your measurements is if you have the open path LI-7500. If you have a net radiometer that does the 4 components, you can use the shortwave and longwave measurements and model the sensor temperature, and that helps with doing the correction for for surface heating. All right, so we've talked through all the sensors. Now we want to talk about how do we monitor and record all this data. Typically, you want to be able to use a data logger. The one here shown is manufactured by Sutron. And you want to have an enclosure you can drop that data logger into and protect it from the elements, and also be able to wire in all the sensors. So we've covered a lot of sensors, and to make sure you get the full suite of the correct Biomet sensors, we've at LI-COR put together several packages based on common use cases that are in the Eddy Covariance community and determined by the scientists here as well. Each of these have pre-written programs, installation guides, and again, Israel will talk a little bit more about this in his portion and how these programs are preloaded on data loggers. Inside the enclosure, you want to try and have things as easy as possible. The one that we've developed here is pre-configured. Most of the wiring is in place. Virtually plug and play with the directions. You notice there's some relays in there. Those are automatically included in the systems in case someone wants to add those self-calibrating heat flux plates if they want to do that. Some of the other components are important to have inside there. Maybe are circuit breakers to help protect the data logger, and another one for the sensor circuit. There's also power distribution and grounding terminals included. If you want to add additional sensors, there's analog input modules that allow you to connect additional sensors. Each of these have about 10 channels with a 16-bit resolution. Okay, we have one more question from the audience, it looks like. I'll go ahead and take that now.
Yes, we do have a question. It's how many sensors can be added to a Biomet system?
Okay, good question. This particular data logger has 5 differential, or you could say 10 single-ended analog input channels. All of those have the 16-bit resolution. And for each analog input module, it provides another 10 channels. And the system's been tested up with 20 additional modules. And so that gives you the potential for an additional 100 differential or 200 single-ended analog input channel measurement channels. Okay, let's keep going here. So for the system, it's a good idea to have an Ethernet network connection. There's an Ethernet port that we use to connect the data logger and all that data to our LI-7550. That gives us synchronized integration of the Biomet data and the Eddy Covariance data. There's room in the box we provide. If you want to add a network switch, perhaps you want to add wireless communication modules, you can do all that. And in the end, what we're doing is we're bringing this all together. We're taking this Biomet data, putting it together with the Eddy Covariance files in our GHG files. Israel's going to talk about that right now. And then these files are easily fed into EddyPro 4, where all the computations are done. So I'm going to go ahead and turn it over to Israel. It looks like while we're switching over, there's a question from the audience. Thank you, and I'll let Israel take it from here.
Thanks, Dave. I do have one more question for you. And while Israel takes his seat, I'll go ahead and read that. It is, can a user add their own sensors and or create their own program? Israel, do you want to go ahead and answer that for us?
Thanks, Dave and Ashley. To answer the question, This may become more clear as we go with the presentation here. Yes, it is possible to add your own sensor and to configure it differently. We do include the instructions on how to do that so that the integration that you have with the Biomet and the LI-7550 goes on, and we'll talk a little bit more about that. So I'm going to continue with the rest of the session today, and I'm going to talk about system integration. So Dave mentioned, and he talked a lot about why we need Biomet measurement. So let's talk about how we can integrate these types of sensors into our current or new EC sites. It may seem quite a challenge at first, but the solutions we'll talk about will make this very practical and feasible. So I want to start by discussing or clarifying what are the key points to consider for a well-integrated system. As we've seen, Biomet systems add multiple sensors to an EC site. Typically, additional sensors are logged separately and at a lower frequency than the high-frequency gas and wind measurements. It is also common to have a separate data logger dedicated for these sensors, the Biomet sensors. Ideally, it makes a lot of sense to put the data from the Biomet and Eddy sensors in the same location. In addition, it's quite beneficial to have the Biomet and high-frequency data on the same time scale. For example, if the high-frequency data is recorded on a 30-minute scale and the Biomet is on a weekly data file, then it may be a bit difficult to do the data processing, having to go back and forth in that 1 week data file. In addition, most importantly actually, both high frequency and Biomet data should have metadata describing what type of sensors and what units are being used, how the measurement is made. So this information should be logged along with the data to make data processing and reprocessing, as is the case with Eddy Covariance, straightforward. So the goal in simplifying and integrating an EC site is to have the system that is well integrated and facilitates the measurement, the data analysis, and maintenance of the site. So in combining the Biomet data, we would like to have a straightforward Biomet and high-frequency measurements and collection system. We also want Biomet and high-frequency data logged in a self-explanatory manner for easy data processing. That is, we should have metadata with each data. And in addition, we want Biomet quantities calculated or computed from the measurement on the same averaging period as the flux, because in the end, we want to compare and analyze the data that we have from the flux and the Biomet station. So the system that we talked about, this well-integrated system that we talked about, is achieved by the interaction between the LI-7550 analyzer interface unit and the Biomet station. Dave has mentioned a little bit about the Biomet station, the data logger, what's included, what sensors. I'll talk a little bit more about the LI-7550 and what the interaction between these two components to make this integrated system feasible. So the protocol they interact over is over Ethernet. We have worked on the interaction between these two systems over the Ethernet. So that allows you to put the Biomet station further away from the tower, because you can have longer Ethernet cables. And you can put your Biomet station somewhere in your footprint and still be able to achieve this integrated system. So one of the key components of that integration is the pre-programmed packages that LI-COR offers. And LI-COR offers this pre-packaged or pre-selected suite of sensors based on what we've seen from different EC sites from our communication and interaction with customers. And not only do we pre-select the sensors so you can get a specific package, we also have a pre-written program for each package that you can order. This pre-package order or pre-package pre-selected package includes the installation guides, and also like the question we mentioned earlier, the instructions to add a sensor, how the how to add a custom sensor or how to add more of the sensors that are included with the package is described. So this pre-written program is already loaded into the data logger. So this pre-written program handles data collection, and it also handles data communication between the Biomet station and the LI-7550 analyzer interface unit. So the analyzer interface unit, most of you, if you have our new OpenPath and enclosed path analyzers over the last couple of years, you probably are familiar with this unit. It's the unit that integrates the data from gas analyzer, and also if you have any GHG systems, it also integrates data from our methane analyzer, the LI-7700. Now this unit is also going to be integrating the Biomet data from the LI-COR Biomet station. So as you can see here, the LI-7550 has multiple communication pathways that that it uses to achieve this integration. I've got the Ethernet, as I mentioned. The Ethernet is used for Biomet station interaction and also for methane analyzer. You can integrate your sonic measurements using the analog inputs or the auxiliary inputs, and obviously the CO2 and H2O data comes through the ERGA connection here. This 7550, the analyzer interface unit, also allows you to beam data to data logger through SDM and other outputs like RS-232 and Ethernet. In addition to this interaction and output, the 7550 is also where data measured from gas analyzers and the Biomet station is stored. It has a USB connection that allows the use of a 4 GB USB, and if you need it, a 16 GB optional USB. So the 4 GB is not just 4 GB because it is expanded by the compression that the LI-7550 does. So when data is being collected from both the high frequency analyzers and also from the Biomet station, it's going to be collected at your specified flux averaging interval or your data collection interval, let's say 30 minutes. And at the end of every 30 minutes, it's going to be compressed into a zipped format called a .GHG file. And we'll see what that .GHG file contains in a little bit. So the other issue we talked about is, we want to make this simple, straightforward setup. So the analyzer interface software is Windows-based software, which is very straightforward to do the site setup, to do the integration of the methane analyzer, Biomet sensors, and setting up your site parameters. As you can see here, we've got the main window of the analyzer, and we've got different variables being shown, and we also have some diagnostic information about the site and different things we've got integrated to the system. If we look further through the different dialogues, we also see the Biomet station integration tab, where we choose this which Biomet station we want to integrate with this EC site. We can see what variables are being logged. We have an option to synchronize the clock of the LI-7550 and the Biomet station, and we can look at how much data has been logged, how much free space we have on the USB. As you can see, there are more tabs here to do the methane integration, the anemometer integration, and a place to enter the site description so that metadata can be collected with the measurements. So once we set up the site, we will start collecting GHG files. These files, as I mentioned, are archive or compressed files that contain high-frequency flux measurements made by high-frequency gas concentration and temperature, sonic temperature, and wind speed measurements from gas analyzer, sonic anemometer. And also they contain Biomet data, sensors like soil heat flux plate, net radiation sensors, air temperature sensors, relative humidity sensors, and they're all zipped together on every half hour into this GHG file. So if we take, I have here a bunch of GHG files from a sample data set. If we take a look inside one of those GHG files, we see 4 files at the moment. As you can see, there are 2 data files and 2 metadata files. And as I mentioned earlier, the gas analyzer and the sonic data is one data file, and it's on collected at high frequency, typically 10 Hertz or more, and it has its associated metadata. And the Biomet data, which is collected typically, at a much lower frequency, once a minute or so, is collected here or denoted here as Biomet data, and it also has the Biomet metadata that describes what each variable is and how it's collected, what units it uses. So what this allows us to do is to take the data with the associated metadata during processing in EddyPro. I'm going to throw a poll question here before I move on to the next section.
Thank you, Israel. Our second poll question is, if you currently process EC data, what software are you using? And again, there are 5 choices. Go ahead and select your answer and hit submit, and we'll give everyone just a couple of moments to finish. All right, it looks like most everyone has submitted an answer. Thank you. And we'll go ahead and let Israel move forward.
All right, thank you for your participation. EddyPro has been out for about a year and so now. It's come from the European project IMEC, and we've gone through a couple of revisions of the EddyPro software. We are now at version 4, and version 4 has many advanced additional features, new features that are very useful, very interesting. But on this presentation, I'm only going to talk about just the Biomet integration. And in the next webinar, well, actually not the next webinar, but the webinar after next, Gerardo will help us navigate through EddyPro version 4, and he will tell us more about the advanced features and the new additions in the software. So for those of you that are familiar, this is the welcome screen on EddyPro 4, and to process data, any flux data, you create a new project, and when you create a new project, you get presented with this screen that has different options to select what type of data you're processing. If you're processing a LI-COR GHG file, the selections are very much done automatically, so you don't have to do a whole lot of work. Especially for this case, we've stayed consistent with that protocol. If you have a LI-COR Biomet system with high frequency eddy data being collected and Biomet data being collected by the LI-7550 into a GHG file, the only thing that you have to do in EddyPro to include that data in your data processing is to click on this Biomet data checkbox here. The Biomet data is embedded in the GHG file, so you don't have to do any more work to have the Biomet data and your flux data processed in a similar manner on the same time scale. If you don't have a LI-COR system, EddyPro 4 still allows you to use your external Biomet data when processing your flux data. However, there's a certain format you need to follow so that your Biomet data from another system is formatted in a way EddyPro can understand and interpret what's contained in those files. So there are a couple of options to do this. You can use one large file that contains all your data, or you can use multiple files that contain your Biomet data. For more help, you can click on the question mark here, and it tells you how to pre-format your data for use in EddyPro. But if you have a LI-COR Biomet station, none of that is needed. You click on that checkbox, you move on to the next page, the data selection page. The data selection page is where the GHG files are read by the software EddyPro automatically, and all the variables that are needed for flux computation are selected. You can see on this window that I have gas concentration from LI-7500A, the open path CO2 H2O analyzer, and methane concentration from the open path LI-7700. And in addition to that, I also have ambient temperature, relative humidity, global radiation, long wave incoming radiation, things like that that are coming from my Biomet data. This is done automatically. The software can find the right information because the data and metadata are coupled together. The software can find the right information from the data and select it for flux computation. So at this point, I only need to click on a few different settings on how I want to process my data and can proceed with running. After a run is complete, I get a full set of outputs from EddyPro. EddyPro has increased the number of outputs from the previous versions. We've included co-spectra and full spectra outputs, binned ogives, binned co-spectra. We've also included ensemble spectral outputs, and we will talk about all of these in the third webinar in this series. And also you have the outputs that are familiar since the first version, the AmeriFlux output, the GHG Europe output, the full or the rich output. These outputs are flux data from the high frequency measurements, formatted for different submissions, for AmeriFlux database or GHG Europe database. As you can see here, I have the full output. The full output contains all the fluxes from the high frequency measurement. In addition, I also have an output titled Biomet. This is where I get all my Biomet variables, Biomet quantities computed, averaged over that flux averaging period, screened for reasonable values, and output on the same time scale as my flux computation. So that makes my life a lot easier to compare. For example, when Dave was talking about energy balance, now I have every component in that energy balance equation in the data. So all I need to do is compare the correct quantities or variables at the same time scale and decide how close or how far away from the energy balance closure my site is. So let's look at some results. Here is the results for gas analyzer data. Fluxes, you see CO2 and H2O fluxes. You see sensible heat and latent heat fluxes, so some energy fluxes and some scalar fluxes. And from the Biomet output, you get some energy fluxes, for example, net radiation here in the red, and in the blue we've got soil heat flux. And on the right y-axis I have PPFD. So these are the outputs from the Biomet station, and they're averaged for 30 minutes, similar to the flux averaging period. So in this manner, the integrated system allows you to compute fluxes and have the Biomet output in the same time scale without much work in programming the data logger or setting up the site in a straightforward manner. So this integration happens because we've got the packages and the pre-written programs for the Biomet sensors, that are preloaded on the data logger and are able to communicate with the LI-7550. All that data, along with the sonic and high frequency measurements, are compressed in the .GHG file, and along with metadata describing the data, EddyPro can read those files very easily, very quickly, and process it according to your settings to give you the final results, computed, well-corrected fluxes. So that brings us to the end of this presentation. Before we finish, I want to point out what is coming up in the next webinar. We have Eric and myself presenting the next webinar, Biomet Sensors for Eddy Covariance. We'll talk about the different sensors included in the packages we mentioned earlier. We'll talk about detail, what kind of sensors they are, how they perform, how they need to be set up in some detail. And we'll also dig a little deeper into the LI-7550 software, how you set up your site, how you set up your metadata, and things like that. As I mentioned, EddyPro 4 webinar will be the next after the Biomet sensors. EddyPro 4 is now available on our website, so you can go to LI-COR.com/EddyPro to download. We also ask your participation on the EddyPro forum. There have been a few questions over the last couple of months that we've been discussing. So we encourage your participation on the forum. If you have questions, if you have features, or if you notice any bugs or problems, also we would like to know. So just a reminder, we are continuing with our 3-day Eddy Covariance training courses at LI-COR. So you can go to our website to register for the next available training date. This is just a reminder again for the previous Eddy Covariance webinar series that we did last year. There were 5 webinars, so you can find a lot of useful, helpful information in those webinars.
Thanks, Israel, and thank you everyone for your participation today. You had some good questions, and thank you for submitting your answers to our poll questions. We do not have time right now to take any more questions live. However, if you do have a question, you can go ahead and submit that via the Q&A panel, or you can email one of us, and we will get back to you as soon as possible. We will stick around until all of the questions submitted via the Q&A panel have been answered. So thank you, and we look forward to seeing you at our next webinar.